Greetings, math friends. This is going to be lecture 1 for Introduction to Limits. With that being said, I quickly want to just talk about where we are in kind of the hierarchy of mathematical concepts. As we look at the number sets that we could study and that you have probably been exposed to up through an Algebra 2 class, we typically see the foundational theories behind calculus studied with real numbers and complex numbers. If you look at university catalogs, you typically see things like introductory real analysis and introductory complex analysis. And that just gives you a hint on which number set that you're really going to be working in as you study those concepts in those classes. For what I'm going to be talking about in this series, we are going to be sticking with the real numbers. So hopefully the majority of you are pretty comfortable with the real numbers at this point. So this is going to include numbers that you can count on your fingers. It's going to include the number 0. It's going to include all the negative versions of those numbers. It's going to include decimals and fractions. And it's also going to include the irrational numbers like pi and the square root of 2. So all of those numbers are game to be used in our discussions. One of the first things that we want to do is I want to start to give you an idea of what a limit is, give you a visual illustration, give you a geometric conceptualization, and a formal definition. Hopefully with a combination of all of these things, we will be able to convey the beginnings of the ideas of what we're talking about when we talk about a limit. So this is a really important concept in how calculus works. The underlying theory that we have accepted as a rigorous model for calculus working mathematically and logically. All right, with a limit, we want to describe the behavior of x in a single variable function as x is getting closer to some given value. All right, so that's the beginnings of the idea of this. So as x gets closer to some given value, we will see that the corresponding image of that value, the y value, the functional value, that also is approaching something as x approaches something. One of the concepts in calculus that we have to get used to is that when we approach a point, like as a limit, it could not actually be a part of the function, so it's missing from its domain or range. But we can still approach that, and we can get really close to that point without it actually being present. And we can just inch closer and closer to that point. It doesn't have to actually be there for me to know that I've approached that essentially hole in the graph, just like I can approach the edge of this hole without actually falling in the hole or standing in the hole. This is an idea of approaching a point in a graph. The point doesn't actually have to be there for us to know that we can approach that location. And that's exactly what it is from a geometric perspective, a location in a geometric space. All right, so let me give you a bit of a geometrical representation of this. So, starting with our x and y axes here that we are familiar with probably from Algebra 1 and Algebra 2. If I have some function here we will call f of x. Then I'm going to choose some value, say c here. And then I want to know what happens as my x values get close to that. So if you think about, if you make an XY table in like an Algebra 1 or an Algebra 2 course, right? You choose an X, you plug it in the function, you get back a Y value. More precisely, some of you may have done this as an X and f of X table. So I have this value C here, right? And I want to know what is the associated Y value here. So this is f of C, because it's a function. I plug this value in for x because it's on the x-axis, and I get some functional value back. This is f of C. So what if I choose an x value over here? So this is x minus some other value, some tiny value. Let's call it delta. So if I have this x minus delta here, this is smaller than c. All right, so x minus delta. As I plug that in to the function, well, where is that going to be? Well, if I come up here graphically, I can just come over here and I'll have some value here, f of x minus delta will be right there. Right now, this is very abstract. I'm not using actual numbers in this. So I have this value here. I could have gone on the other side here, on the right-hand side of C, and I also could have chosen, say, the same delta, but I add it to C. So this is some x plus delta. And that's over here. And then we see that that value actually is larger than the f of c value here. So we can also sandwich that c value in between these two values. So these are two values that I've chosen, but I want to choose a variety of values. This is a function. The way I've drawn it, it's continuous. So we have lots of numbers to choose from. We are talking about real numbers. So this number set has infinitely many numbers in here. Lots of numbers and values to choose. If I choose a smaller number between this value and this value, I can see where that falls up here. So I can come up with more and more numbers between this value and the c value that I said was my value of interest. Likewise, on the right-hand side, I could choose a number smaller than x plus delta, but larger than c. And I have this kind of narrowing, focusing in. So I want to see, as I get closer and closer to C, as I complete layers of this sandwich, what is happening with this category here, this column, which we used to call Y in Algebra 2, but we may be now calling the f of x category now. These are the functional values that I get out when I plug these x values into the function, whatever it is, and I get these values back. So is something specific happening here? Is there a pattern? Okay, as the numbers that I choose get closer to C, what value is f of C really? Again, I've not chosen any actual numbers so far. This has all been very abstract. but I'm trying to get closer and closer to this value c. Now, another thing that will potentially throw people off is c doesn't actually have to be there. I can get close to the number that should be there, but since I don't actually need to get to the number doesn't have to be there. So there, in other words, can be a hole in the graph. That c value doesn't have to be there. We can represent that pictorially by putting a little circle there to just show that nothing is there. We could just put that circle in there and say, like, as I get closer and closer to this value, what will this value be, the f of c value be? I've got this open hole here. I'm getting close to it, but I don't actually have to jump in the hole. I'm just getting close. That's what we mean, kind of from a geometrical argument of the idea of a limit. We are approaching this location in geometric space, but we don't actually have to arrive at the location. We want to now take a formal look at limits by looking at the definition. We are going to define the limit with this notation where we write lim above the variable as it approaches the number that we had stated previously as the number we were interested in, acting on this function, which is the function f of x, and then that is going to give us a value, a functional value, a y value, and that's this value which I had previously called f of c. As I plugged c into the function, I got f of c, and now I am calling that value a here. This is a real number, and that's stated here in the definition. So a is a real number that f of x approaches when x is close to but not equal to this particular value we called c. The function has to be defined to the left and the right of the value, but it does not need to have c within its domain. So that's our formal definition, and that essentially does what we have demonstrated previously. So now that we have this formal definition, we have this diagram that goes with it, we want to apply it to some function. So perhaps we want to go with something that we are familiar with. So let's start off with, let's define some function, say x squared. This is a function that you hopefully have been introduced to as early as your Algebra 1 course, if not sooner. So let's talk about the properties of this function. The domain for this function is all real numbers. Okay, so we are securely in this real number realm. And when we look at the definition here, any value that I choose here is in the domain, even though it doesn't have to be in the domain. And furthermore, to the left or the right for any of those numbers, they are also going to be defined in the domain of the f of x that I've chosen here. We could talk about the range of this also. The range is not all real numbers. The range is actually, for this particular one, the range f of x is going to be greater than or equal to 0. So not all the real numbers. So we have the upper plane and we have all real numbers for the domain. All right, so let's choose a value to look at this. Just arbitrarily, let's say that x is going to approach 1. All right, so what's the limit of x squared as x approaches 1? Well, we've already discussed that this number is in the domain, and any number that I choose to the left or right of that is also in the domain. So in this case, the easiest thing that we can do when we know these properties of the function is just simply plug this value into this function, and that's going to be the value that the limit approaches. So in this case, it's also 1. So earlier, I did an argument by geometry as part of the lead up to this. What can we do with geometry? Well, if you know how to graph this, you could graph this. So we have this U shape here. If we choose 1 here, and we go up, what is the value here, the y value, when we go straight up from there? Well, that value is going to be defined according to the function. So as we go up from 1, the output is 1. That's exactly what a function does. Let's talk about a number to the left of 1. So in a relatively big jump, we could look at 0. If I plug 0 into here, I get 0. And if I plug in 2, I get 4. So in a step of 1 unit away from 1, then I'm looking at 0 and 1 in the x direction and 0 to 4 in the y direction. If you remember back in my discussion earlier, I said x plus some delta. In this case, the delta, the jump that I'm making right now, is 1 also. My c value is 1. When I look at my x direction, letting delta be 1, I'm stepping back 1 unit, which is 0, and stepping forward 1 unit, which is 2. And as I plug those values into the function, I'm looking at values between 0 and 4 in the y direction. So this interval appears to be a little bigger interval than what this interval appears to be, but all of these values will map into values into here. And I can choose a smaller delta if I want. I could choose half, so that I'm only looking at values between a half and 1.5, and I'll get values still falling into this range, but actually I can make that range smaller and still capture all of these values. And then I can make delta as small as I want arbitrarily. I just, by the definition here, I don't want my delta to be 0 because I don't want that my c value 1 here to be the only value in my interval here to meet this definition. So I'm squeezing this here. I'm getting closer and closer to 1 without being just 1 here. And as I squeeze this, this naturally contracts. So where does this squeeze into? That value that this squeezes into is what we're saying is the limit value. So as x approaches 1, this squeezes down and approaches 1 also. Right? So let's do one more example with this definition with this kind of scenario. All right, not a big change. I'm going to the polynomial whose degree is next highest, so a third degree polynomial now as opposed to a second degree polynomial. And again, arbitrarily, I'm going to approach 2 this time. Looking at a sketch of this, we see this kind of a graph here. The domain and the range in this situation is both of these are all real numbers. So we're not going to step outside of our domain and range when our focus is the real numbers. Our c value, which is 2 in this case, is a part of the domain. And then all values to the left and right of c are also going to be in this domain. So again, as I explained before, at this point we can just plug this value into the function, and that is going to be the limit of this. If we come over to here to wherever 2 is, we are looking for the value that the function takes on, and we can choose a number smaller than 2 and a number larger than 2, and it will take on values as well. And then as we squeeze that, we want to know where the y value is squeezing into. So it's essentially as easy as plugging 2 into here. So 2 to the 3rd power. 2 times 2 is 4. 4 times 2 is 8. So this value is 8. And it does make sense that this value is a bit of a magnitude larger than this because we are cubing this. It's multiplying this value by itself 3 times. So that is the basic introduction to limits and having multiple representations, a formal definition, and then a couple of examples of application. Go ahead and try some of these problems at the end of the video, pause, and then start the video again and check yourself with the solutions. Cheerful Calculations.